So in section 6.5, we're going to learn how to name hydrocarbons. And this is very important as it helps chemists to communicate across different languages, across time zones. Knowing how to name them is essentially the language of organic chemistry. And every organic chemist will speak the same language then after learning how to name hydrocarbons. So every organic compound has a name formed by systematic rules made by IUPAC, the International Union of Pure and Applied Chemistry. Many compounds also have a common name. And typically the IUPAC name is composed of three parts: the prefix, the root, and the suffix. And so we're going to put those together. Basically the root will be defined by the number of carbons, prefixes will indicate the types of branching, and the suffix will indicate any functional groups present in the molecule. An example of a chemical name. There are many ways to represent an organic compound. For example, ibuprofen. Here's the skeletal line structure. We might have a few different functional groups in here that we haven't learned about yet. The brand name, Motrin, Advil. Generic name, ibuprofen. According to IUPAC rules, it's called 2,4,2-methylpropyl phenylpropanoic acid. And we'll learn those rules. We typically won't name compounds as complicated as this, but we will learn how to use the IUPAC rules. It has a chemical formula, and it can be considered, or it can be cataloged by a type of drug, an analgesic. So naming simple hydrocarbons, those are the easiest to name if they have no branches. The basic rules are assigning the root, telling us how many carbons are in the chain, and then assign a suffix that tells us the category of hydrocarbon: alkane, alkene, alkyne. And if there are multiple bonds, we'll assign a number that indicates where those multiple bonds are. So table 6.4, this would be a good table to memorize. Shows us the IUPAC names and the condensed formulas and the skeletal line structures for the 10 simplest straight chain alkanes. If there's one carbon, we call it methane, 2 carbons ethane, 3 propane, 4 butane, and after we get to 5 carbons, then the names proceed in a more logical manner: pentane, hexane, heptane, octane, nonane, and decane. They all have a prefix, or the first part of the name indicates the number of carbons. 1, 2, 3, and 4, they're not as logical, but then we get to pent, hex, hept, oct, non, and dec. Those all indicate 5, 6, 7, 8, 9, and 10 carbons. Condensed formulas we've discussed. The skeletal line structure, simply an extension of the zigzag line, given an increase in the number of carbon atoms. And each type of hydrocarbon has a characteristic suffix. Ane is used for alkanes, so methane. Ene is used for alkenes. Ethene tells us that we have a 2-carbon alkene. And acetylene, or ethine, is used for alkynes, Yne. So we just changed the last 3 letters of the name to indicate whether there is no double bonds, or triple bonds present. So if there are multiple bonds, we then number the carbons in the chain in order to indicate the location of those multiple bonds. We number the chain starting from the end nearest the multiple bond, and then the number of the first carbon of the multiple bond is the locator number, sort of the address of that multiple bond. And if it's a double bond, we can add cis or trans prior to the locator number to indicate whether it is a cis or a trans double bond. For example, here we have the 2 isomers of butene. 1, 2, 3, 4 carbons implies butane. We change it to butene because we have an alkene. And now if we number the carbons, 1, 2, 3, 4, we notice that the alkene resides on carbon number 2. And this is the cis version. Both heavy groups are on the same side, so we call this cis-2-butene. This is different from trans-2-butene, which has the heavy groups on opposite sides of the alkene. Another example, this one has 1, 2, 3, 4, 5, 6, 7 carbons. It's called heptane. We change it to heptene to reflect that there is a double bond present. We start numbering from the end nearest the double bond, 1, 2, 3, and we call it 3-heptene, telling us that the double bond is off of the 3 carbon, and this is the trans version of 3-heptene, an imaginary line parallel to the double bond, heavy group on one side, heavy group on the other side, so trans 3-heptene. Here's the numbering for the heptene. Naming cycloalkanes, the root is simply the number of carbon atoms in the ring, and we add the term cyclo to the front of the root name to indicate that it is a cycloalkane. 3 carbons, propane. Here's the skeletal line structure. We change it to cyclopropane. 4 carbons is butane. Skeletal line structure, cyclobutane. 5 pentane, cyclopentane. Cyclohexane, cycloheptane, and cyclooctane. So let's do a few practice problems together. So we want to write the structural formula, condensed structural formula, and skeletal line structure for the following straight chain hydrocarbons. So now we want to translate the name into the 3 different drawings that we learned about. So octane, OCT, oct means 8 carbons. We need to fill them in with hydrogens. This may take a few minutes. Sorry, that bond should be like that. And then when we're done here, we want to draw the condensed structural formula. That's where we draw CH3, and then we have 1, 2, 3, 4, 5, 6 CH2 groups. So in parentheses, we can put that CH2, 6 of them, and then one last CH3. So it's a much simpler way to draw the condensed structural formula. And then the skeletal line structure is even simpler. We just need an 8 carbon zigzag line. 1, 2, 3, 4, 5, 6, 7, 8. Done. That's octane. Very easy to draw these skeletal line structure. Pentane, 5 carbons. Expanded structural formula. Condensed structural formula, CH3, there are 3 CH2 groups, and the last CH3. Skeletal line structure, we need a total of 5 carbons, 1, 2, 3, 4, 5. Done. Moving on to 3-octyne. So here we see 8 carbons. YNE implies an alkyne, and that's in after the 3rd carbon. So if we draw the expanded structural formula, we get to the 3rd carbon, we need to draw the alkyne. 5, 6, 7, 8. Again, filling in hydrogens. When we get to the alkyne, we need to consider how many bonds the carbon has already. This carbon has 3 bonds and 1. It doesn't need a hydrogen. Neither does this one, so we move on to the 5th carbon. The condensed formula, CH3, CH2, C, and now we can just draw another C if we want to. CH2, 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 CH3. You could also draw it this way. If you wanted to make sure that it was understood that there's a triple bond there, that might be more clear to beginning students. And then the skeletal line structure, after the 3rd carbon, we need to indicate a triple bond. So 1, 2, 3. And remember that triple bonds are linear, so we need to keep drawing that downward. Here's the 4th carbon, 5, 6, 7, 8. So there's 1, 2, 3, 4, 5, 6, 7, 8 carbons in this drawing. 1-pentene. So we need to draw 5 carbons in a row. ENE implies alkene in the 1 position, so it's right here. So then we need to fill in hydrogens. This carbon only needs 2 more. This one only needs 1 more. 2 for this one. 2 for this one. and 3 right here. The condensed formula, CH2, if you want to indicate that double bond, that's fine. Make more clear. CH2, CH2, CH3. The skeletal line structure, 1, 2, 3, 4, 5. Put the double bond in at the first bond, the first carbon. And part 2, name the following alkynes. First we start by defining the root. So 1, 2, 3, 4, 5, 6. 6 carbons is hexane. It's an alkyne, so we call it hexyne. Then we need to indicate where the alkyne is. Start by numbering at the end nearest the alkyne. We don't have to number any farther because it's on the 1 carbon, so we call this 1-hexyne. And that's what this structure is. Over here, we have the skeletal line structure. We need to count carbons. 1, 2, 3, 4, 5 carbons. So it's pentane, but because it's an alkyne, it's pentyne. We need to start numbering by the end nearest the alkyne. That's going to be the right end. 1, 2, 3. We don't have to number any further. The alkyne is nearest to carbon 1. So again, it's 1-pentyne. What is the correct IUPAC name for the following alkene? First thing to do is count carbons. 1, 2, 3, 4. So it would be butane. We change it to butene because there's a double bond present. And we number the carbons starting with the end nearest the alkene. 1, 2, 3, 4. So 1 is attached to the alkene, so this would be 1-butene. Not 2-butene because it's between the 1 and the 2 carbons. We always use the smallest number possible, 1-butene. Okay, so now let's get into naming branch-chained alkanes. And here we have to add some additional rules, and a branch along the main chain is considered a substituent. So we call it a substituent. The prefix to the name identifies the substituent as well as its position. So this is sort of identifying what is attached to the chain and where it's attached to the chain. And so the rules are these 6 in order. It's going to seem like a lot of rules all at once, but once we do a few practice problems, I think you'll find that it's reasonably straightforward. It's pretty intuitive once you get the hang of it. Certainly you can look up these rules in your book and reread them. You can replay this video as many times as you need if you find that we're going too fast. So the first thing we do is find the main chain in order to assign a root name. We've already had experience with that. Determine the class to assign the suffix. We've already done that. Alkane, alkene, alkyne. The next step is slightly new. We need to name each substituent according to the number of carbons in that substituent. And then we need to assign each substituent a locator number. We've already had some experience numbering carbon chains. Then we put together the prefix name, the number plus the name of the substituent. And then we assemble the entire IUPAC name. So the main chain is going to be the longest continuous carbon chain. It will also contain a multiple bond if present. And this chain determines the root name. And be careful assigning the main chain, because if there are branches, the main chain might follow a branch. Remember, we want to get the longest continuous carbon chain. So for example here, the main chain is outlined in pink. It's 7 carbons long. It is not this 5 carbon chain on the bottom here, because that leaves us this 3 carbon branch, and if we count a different way, 1, 2, 3, 4, 5, 6, 7, we get a 7 carbon main chain. Another way to draw it is with this expanded structural formula here, 7 carbons, and the 4th carbon has a branch. So it's not this 5 carbon chain. That would leave us with a 3 carbon branch and not the longest possible main chain. And it's not this 5 carbon chain on the side here. That would also leave us with a 3 carbon branch. If there's a double or triple bond, the main chain must include it, even if this results in not the longest possible carbon chain. So in this case, the best or the only main chain can be this 4 carbon chain because it includes the double bond, even though there's a 2 carbon chain here and we might have 4 5 carbons across. So this would be incorrect over here. It doesn't include the double bond. So we want to include the double bond This is the correct way to number, even though it only has 4 carbons versus 5. Assigning the suffix. We've seen this already. This identifies the class of hydrocarbons. Use ane for alkanes, ene for alkenes, and yne for alkynes. Now we get into rule number 3, naming the substituents. Each substituent will have a name based on the root names, according to the number of carbons it has. We'll change the root name from ane to yl to indicate that is a substituent and not a full molecule. So an example, if a substituent is a 2-carbon chain, the root name is ethane, but we change it to ethyl to indicate that it is a part of a molecule, not an entire molecule of itself. So here's an example. We have the main chain here, 1, 2, 3, 4, 5, 6. There are 2 substituents, a 1-carbon substituent and a 2-carbon substituent. 1 carbon is methane. We change ane to yl to get methyl, indicating a 1-carbon substituent part of the molecule. A 2-carbon alkane is ethane. We change it to ethyl to indicate that it is a 2-carbon substituent part of the molecule. So methane changes to methyl, ethane, ethyl, propane to propyl, butane to butyl, pentane to pentyl, and so forth. We change ane to yl to indicate that these all describe substituents, parts of molecules, whereas these describe an entire molecule. So decyl describes a part of a molecule. Then we need to number each carbon atom in the main chain, beginning from the end of the chain closest to any multiple bond. Otherwise, we'll start numbering from the end nearest a branch point, so either closest to a multiple bond or closest to a branch point. So for example here, we have this 6-carbon chain, and we have 2 branch points on the 3rd and 4th carbon. So in this case, it's not quite important which side we start numbering from. 1, 2, 3 gets a branch point, 4 gets a branch point, 5 and 6. If we numbered from the left, 1, 2, 3 would have a branch point, 4 would have a branch point, 5 and 6. So in this case, it's a little ambiguous as to whether we would number from the right or the left. And then we label them. This is a 4-methyl group. It's on the 4th carbon. It's a 1-carbon group. We label it 4-methyl. 4 is the locator number. Methyl is the identity of the substituent. This is 3-ethyl down here. And then we place the substituent names in alphabetical order. So ethyl goes before methyl, and that's the reason we'll number from the right in this case, so that 3 is in front of 4. We wouldn't want to have 4-ethyl, 3-methyl here. So we place the locator number in front of each substituent name, 3-ethyl-4-methyl. That is the prefix for this molecule. If we have more than one ethyl group or more than one methyl group, we would insert an additional prefix, di, tri, or tetra, to indicate how many ethyl groups we have. So in this case, we actually have 4 methyl groups, 1 on the 2-carbon, 2 of them on the 3-carbon, and 1 on the 5-carbon. So we have tetramethyl to indicate 4 methyl groups, and then we put all the 4 locator numbers in front of tetramethyl. So we have 2, 3, 3, 5. We have to have 4 numbers if we have tetra here to indicate there are 4 methyl substituents, and these numbers indicate where they belong. So the last rule then, assemble the IUPAC name. Put the prefix in front of the root and put the suffix at the end. Separate numbers from letters with a dash, and separate numbers from other numbers with commas. So for example, our example here was 3-ethyl, 4-methyl, and we put the substituents in alphabetical order, ethyl before methyl, and we put their number in front of them, 3-ethyl-4-methyl, no space, heptane, to indicate a 7-carbon chain. So most of the effort going into naming a branch chain hydrocarbon involves constructing the prefix. We spent a lot of time determining that we had 3-ethyl, 4-methyl, so that's where you'll spend most of your time constructing the name. Structural isomers will always have different IUPAC names because they have different connectivity. So if a methyl group moves to a different carbon, it's going to get a different number. And don't let the long and complicated names scare you. The rules are very logical. It's going to get easier as we practice. So let's have some practice. So let's write the IUPAC name for the following branched chain alkanes. So this A we need to number, first identify the number of carbons in the main chain. I think we'll all agree that the main chain is this one, horizontal on the bottom. 1, 2, 3, 4, 5, 6, 7. 7 C's, heptane. Can we keep A and E? Are there any multiple bonds present? No, there are no multiple bonds, so A and E is fine as the suffix. Here we have a substituent. It's 1 carbon, so it would be a methyl substituent. Now we need to identify I like to call it the address of that substituent. We start at the end of the molecule nearest the substituent. I think that they're both equal. In this case, 1, 2, 3, 4. We can call that a 4-methyl group. If we numbered from the other side, 1, 2, 3, 4. So either side is equal. 4-methyl is the location and identity of the substituent. We add that to the beginning of the name, 4-methyl heptane. Normally there's no space here. I have a space just because that's how I wrote the name, but we could rewrite it 4-methyl heptane. So that's pretty simple. We identified the main chain. It's the longest continuous carbon chain. It has 7 carbons, so it gets the name of heptane. We don't change A and E because there are no double bonds present. And then we identified the substituent. It's 1 carbon derived from methane. Change it to methyl to indicate that it's a substituent, and its location is on carbon number 4. This one looks a little more tricky. So at first, we might say it has 4 carbons in the main chain, right here. But I think if we look closely, we can find a main chain with 5 carbons if we follow some branching. 1, 2, 3, that's not right. 1, 2, 3, 4, 5, that would be a 5-carbon main chain. 1, 2, 3, 4, 5. So now we could use either of them. Let's just go with this one. 1, 2, 3, 4, 5. Sometimes it helps to circle the main chain so it's more clear. 5 carbons is pentane. There are no double bonds, so we leave it as pentane. Substituents are here and here. Both are methyl groups. Right, they're 1 carbon. And so we start numbering the main chain closest to the substituents. I think we'll start on the left. 1, 2, 3, 4, 5. Now we're numbering these carbons as we go along. So the first methyl group is on carbon number 2, and the second methyl group is on carbon number 3. And so we have 2 methyl groups. We can call them dimethyl, and we list the numbers 2, 3 dash dimethyl. That's how we indicate the substituents. And now we just put these together. 2, 3 dimethyl. Then comes the root name, pentane. So 2,3-dimethyl pentane. So for this molecule, the main chain, I think, 1, 2, 3, 4, 5, 6, 7, 8 is longer than 1, 2, 3, 4, 5, 6. So we have octane as our root name. There are no double bonds, so we leave it as A and E. The substituent is right here. That is a methyl group. Whoops. Methyl group. Now we want to give it a locator number. We start numbering from the end of the chain nearest the methyl group. 1, 2, 3, 4. Right? It's closest to the right side of the chain. We call that 4-methyl. And then we can list them all. 4-methyl octane. And this last one is the most complicated. 1, 2, 3, 4, 5, 6, 7. We might say that there are 7 carbons. Actually, that one's off the page. Let me move this over. Okay, 7 carbons, but if we start counting from up here, 1, 2, 3, 4, 5, 6, 7, 8. We have 8 carbons as the main chain. So that's the better choice. That's octane. No double bonds, no triple bonds, so we leave it ANE. Now we need to identify the substituents. We have 2 methyl groups, 3 methyl groups, right? Because remember, this is the main chain here. Sometimes it helps to outline the main chain. So in fact, we have trimethyl as the substituents, because we have 3 methyl groups. We need to identify where they are. Starting from the end nearest the nearest branch point, 1, 2, 3, 4, 5. So we have 3, 5, 5 as our locations for the methyl groups. Had we started over here, we'd have 1, 2, 3, 4, 4, 5, 6. So we'd have 4, 4, 6 as our other option. These numbers aren't small enough. They aren't as small, so this is a better choice. So writing this answer here, 3, 5, 3, 5, 5, trimethyl octane. 3,5,5 trimethyl octane. Next question, write the structural formula and skeletal line structure for the branch chain alkanes with the following IUPAC names. So now we're going to go from the name into the structure. Okay, so A, 2-methyl octane. The first thing is to draw the 8-carbon chain. That we get from octane. Then we want to add the substituent 2-methyl. That's located on the second carbon. And it's a methyl group, so we put just 1 carbon on that substituent. Then it's a matter of filling in all of the hydrogens. We have lots of practice filling these in, so we'll do that quickly. Hopefully your drawings with actual pen and paper look a little better than mine with the tablet here. So that's the structural formula. Skeletal line structure is much easier. We need an 8-carbon chain, zigzag, 1, 2, 3, 4, 5, 6, 7, 8. We need to put a methyl group on the second carbon. That's just a 1-carbon group. We just draw a bond up like that. Done. This is 2-methyl octane. So part B, 3-ethyl hexane. Hexane is 6 carbons. So let's draw a 6-carbon chain here. 5, 6. A 3-ethyl group off of the third carbon. Now you can start with this carbon, 1, 2, 3, or you can count 1, 2, 3. I don't care. I typically count from the left if I have a choice. It doesn't matter though. So we draw a 2-carbon branch. That's an ethyl branch. And again, we fill in the H's here. And one more H. So we have 3-ethyl hexane. Drawing the skeletal line structure, 1, 2, 3, 4, 5, 6. That's the hexane. 1, 2, 3. Here's the ethyl group, 1, 2 carbons. Done. It's as simple as that to draw the 2-ethyl hexane. Let me just erase this. This is supposed to be a check mark, not a bond, but I realize it looks like a bond. So here are the 2 skeletal line drawings, and you can see how much quicker those are for making drawings of chemical structures. Clicker question 6-7. What is the correct IUPAC name for the following hydrocarbon? So the first thing to do is identify the longest chain. That's this one on the bottom. 1, 2, 3, 4, 5. That's pentane. And then we have pentane in all of these answers. We need to identify the location and identity of the substituent. Here's a substituent. It's a 1-carbon substituent. Methane turns into methyl. 1, 2. 2 is the locator for this methyl group. So C is the best choice for the name of this hydrocarbon here.